So this is the Kinematics project, and we have our first problem here. You can read it out. So we're going to begin by identifying the given and finds in this equation. So the givens are a sub x is negative 4.905 meters per second squared. And if you want to know how I found this equation value, you can always refer to the video that I've linked below this slide. And velocity initial in the x is 5 meters per second, as stated in the problem. And then we move on to time, which is for our first problem, we want to know the time at 15 seconds. I mean the velocity final of the object at 15 seconds. So our time for this specific problem is 15 seconds. And then velocity initial in the y and the acceleration in the y are both 0 because it's not moving up or down. It's a box moving on a flat surface towards the left. And then find is our velocity final and displacement in the x direction. And we could have wrote delta x, but I just wrote delta r just because. And this is the diagram. So here we have the object, we have it moving towards the left, and this is displacement or the delta x, and velocity final is about right here when it ceases to move. And so here are the equations, and these are the three equations that you need to know in order to solve any of these problems. It does get a little bit more complex towards the like the angled launch problems. However, with this simple problem, we need to focus on these. So I have color-coded the given and finds of the equation. The orange is the givens and the blue is the finds. And luckily, these two are in the correct order, in that the blue is on one side and the orange is on one side, so we can avoid manipulating the equation. However, with this one we would, but we need to figure out in the algebra step which equation we need to use to solve these problems. So I believe that this is the best equation to use for the velocity final problem because it only has the given and finds that is necessary to solve that problem. And then the best equation to use for displacement is this one because, again, it has only the given and finds in the right side of the equation, no unnecessary extra information. So to solve, basically I plugged in the values that were given to get negative 68.575, and it can be a negative number because velocity, it means that the object is moving, is slowing down, so it has like a negative acceleration. Sorry, not slowing down, this should say that the object is moving in the opposite direction than acceleration. And then solve for the second problem, which is finding delta x over the 5 to 10 second interval. And in order to do that, we need to do 5 different things because it's over the 5-second period. So you have to plug in 5 here, 5 here, and this is the only 2 parts of the equation that I'm manipulating, the time values. And I put 6 here, and so on and so forth. And once I get to 10, I add up all the sum. I sum up all of the delta x values to get grand total of negative 2417.528 meters over the 5 to 10 second interval. And then this is our VT graph. So in order to graph this, I used this equation and I just plotted the time from 5 to 15 seconds. Essentially what I have to do is that I have to just change this value. These two remain the same. And then PT graph, I used this equation and I mostly plotted these numbers. However, I did go up and changed till I think 15, changed these t values again. So this is problem 2. Olivia jumps from a low cliff at an angle of 50 degrees above the horizontal with a speed of 2.5 meters per second. Delta y is 6.5 meters. Calculate the following. So we have to calculate 7 things. the identify step. So essentially this velocity initial is given, theta is given, delta y is given 6.5 meters, acceleration in the x is 0 in angle of launch problem, acceleration in the y is negative 9.81, and then v max is 0 for any projectile motion. And these are our finds according to this. So our diagram, so the diagram looks something like this, where this is Olivia and she's jumping off of the cliff. This is delta y max. Then we have our time max around over here, and then delta max around there as well. And then Vy max is also 0 around here. If you were to draw it in terms of a triangle, this is what it would look like. And then the equation step. So here we have the color coded again. So finds are turquoise and givens are yellow. So it's pretty self-explanatory. It's mostly the equations that I referred to in the first few slides. And we move on to the algebra step. So since there are given and finds in this equation, on the right-hand side of the equation, you just plug in the given values to get our delta x. Same with this one. In order to get our this is not delta x, excuse me, this is v initial in the x. Okay, so I changed that. So this is v initial in the x. And since we have everything, all of these things given, we can just solve for, plug in the given values and solve for each for 1 and 2. And then for 3, what I did was that delta y equals to b initial sine theta times time was the original equation, but to get time by itself, I divided by velocity initial and sine theta on both sides to get time equals to delta y over velocity initial times sine theta. And the bolded numbers or equations are the ones that is like what I'm doing. And then v max y equals to v initial sine theta plus ay t max. In order to get t max by itself, I first subtracted velocity initial times sine theta initial from both sides. That cancels this out right here. And then I get v max y minus v initial sine theta divided by ay. So that again, I get t max by itself to get this final equation. And then 5, I use a general equation, which is this right here, and I want to focus more on a specific value of delta y. So that's why I changed it to delta y max. And then for velocity initial in the y, we solved it that in number 2, so we don't really, that's basically a given at this point of the equation. And then focus on a certain time for t squared, so I put t max squared. Those are the only 3 things that I changed in this equation. And then for number 6, all of these things that we need to plug in are already given or solved from the previous equation. So we just need to plug in the values to get delta x. And then lastly, this one, so I begin by square rooting this initial equation over here, and that turns into this. And I added velocity initial y squared plus 2ay delta y because that's another form of this right here. So that's from here, excuse me, that's from here. So I added that to get this final equation. And I also, yeah, that's what I did. And I also squared this whole equation to get rid of this square root over here so that there's only one square root down here. So that is how I solve for that. And the solve is pretty self-explanatory. You just need to plug in the numbers to get your final answers.